Hello everybody, and welcome back to another geometry lesson. Yes, for those of you who are watching from the last one, I am still a little bit under the weather, but we're going to continue with section 9.3. Section 9.3 is all about similar right triangles. So it would make sense for us to start off by mentioning that all of this is going to relate back to our last unit about similarity. Let's start off with the definition of an altitude. So what is an altitude? An altitude is what happens when you have a line segment perpendicular to one of your triangle sides that goes through the opposite angle. Think of it like the height. The height of a triangle can be found by looking at its altitude. So, definitionally, the altitude is a perpendicular line segment connecting one side of a triangle to its opposite angle. A perpendicular line segment connecting one side of a triangle to its opposite angle. That's an altitude. Now, for today's notes, we are going to be using one big diagram most of the time. So, if you don't mind, I'm actually going to turn my notes sideways to make some extra room for this big diagram that we are doing. So here's what I'd like you to draw. I'd like you to draw a scalene right triangle with its right angle being the topmost angle. We're going to call this triangle triangle ABC, but wait, there's more. We are also going to draw the altitude of this triangle. I'll use my purple marker. Going down from point B to a new point, point D. Well, what have we done? Believe it or not, we have created 3 triangles from one. Now you might be saying, Mr. Strager, what do you mean? Well, this is what I mean. If we were to take a look at the 3 triangles in this figure, we have actually made the following. Our original triangle is one of the 3. That's triangle A, B, C. But we have also made a triangle on this left side here. I'm going to shade in red. This red triangle would be triangle, here we go, A, B, D. And we made the third one, you might be able to see it now, on the right side, which I'm coloring in green. This triangle is triangle BCD. 3 right triangles. Not only are these 3 right triangles, but let's take a look at them. ABC has the right angle up on top, but if I was to turn around my paper and look at the green triangle, that just looks like a flipped version of our original. ABC with the short edge on the left, long edge on the right. If we were to reverse this, in fact I think you can see it bleeding through the paper a little bit, we have the same deal. Short edge on the left, long edge on the right. This triangle is similar to our original. Even our red triangle follows the same rules, even though I drew it pretty poorly. The idea is we have just created 3 similar right triangles. That is what the right triangle similarity theorem is. So, the theorem goes like this. If the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original, which also means that they're similar to each other as well. All three triangles are similar. Nice. Let's take a look at an example or two. In exercise 1, we are asked to identify and sketch the three similar triangles in the diagram. And my recommendation is to draw them all facing the same way so it's easier to figure out what is similar to what. So in our original diagram, triangle RST is what we are presented with. But we know that there are two other triangles in this figure. Let's take a look at the green one here. Well, this green triangle, our right angle is not angle T like it is in the original. Our right angle is angle U. So we redraw the new triangle a little bit smaller. So, angle U is the right angle. Now we can start comparing. The short edge of the original triangle was ST. What's the short edge of the green triangle here? TU is the short edge, so T matches with S. And then by process of elimination, angle R is shared by both of them. Nice. Finally, we can draw the last right triangle, which is definitely the smallest of the three. It's this one right here. Well, what's the right angle? It's angle U yet again. So angle U goes here. What's the shortest edge? Well, the shortest edge is definitely from S to U. So SUT is the smallest triangle. Therefore, we can say triangle RST is similar to triangle RTU, which is similar to triangle TSU. Nice. Let's dissect this a bit. So, what this means is, all three of these are similar, which means they're proportional. If I told you that the length of ST was 6 and length of TU was 3, could you find what scale factor exists? Sure you can. We can just do 3 divided by 6 and get 1/3. Or sorry, 1/2. My apologies. 6 times 1/2 is 3. This means we can do further math with it. If the hypotenuse here was 18, well, we can cut 18 in half to get our green triangle length, 9. So this opens up a world of possibilities. A world which we're going to explore here on the next page with example 2. A roof has a cross-section that is a right triangle. The diagram shows the approximate dimensions of this cross-section. A cross-section is just a slice of a roof, for instance. And we have to find the height. There's 2 ways to do this problem. There is a longer but safer way and a shorter but more difficult way. I'll show you both. The longer way to do this problem is starting off the same way we did problem 1. We have to write down what each of these triangles are. So let's do that. Our original triangle has the right angle of y. A short side goes to x, and the long side goes to z. And we also know the measurements. We know that the length of the hypotenuse, the longest one, is 6.3. The length of the short leg is 3.1, because it's the shortest, and the length of the long leg is 5.5. Let's take a look at the other two triangles. Here, we've got our green triangle, which I'm going to star the middle of, on the left side. What's the right angle of the green triangle? Well, the right angle is angle W. What's the short edge? It goes from Y to W. So this is triangle WYZ. We don't know all the lengths in this triangle because 6.3 is the entire bottom of the roof. Our green triangle only covers part of it. But we do know that our height is h, and we do know that our hypotenuse is 5.5. And last but most certainly not least, we've got our red triangle, which I'm going to put a red X in the middle of. What's the right angle? W. What's the short side? Well, W to X is the short side. This is triangle WXY. Again, we know the hypotenuse, but we don't know the height. With this, you've opened up a world of possibilities. We can compare any two things that are corresponding parts, because they will be similar. So let's set up a proportion. Well, I know I want to solve for h. So let's solve for h on the green triangle. What would h be compared to on the black triangle? Well, h and 3.1 are the short lengths. What else could we compare to set up the rest of our proportion? We just need two more numbers. Well, on the green triangle, we only know one other number. 5.5 is the hypotenuse. So let's set it equal to the hypotenuse of the black triangle, which is 6.3. We can solve this for h. All we have to do is cross multiply. So 6.3h equals 5.5 times 3.1. And when we solve all of this, again, you'll need to actually calculate this by multiplying and dividing by 6.3. We get around 2.70 meters. This wasn't the only way to solve this problem. We could have also dealt with the red triangle in the same way. H is the short length of the triangle here. 3.1 is the short length of the bigger triangle. 3.1 is the hypotenuse of the short triangle, or the red triangle. 6.3 is the hypotenuse of the original black triangle. We would end up getting the same general thing. Did I set that up correctly? No, I'm sorry. No, I messed up on this one. I'm so sorry, y'all. H is not the short leg of the red triangle, because look at the diagram. H is the long leg, and I messed up the labeling. So actually, H would not be compared to 3.1. That'd be silly. H is compared to 5.5. I was wondering why the numbers messed up. When we cross multiply, we get 6.3h equals 5.5 times 3.1. And wouldn't you know it, it's the same equation as before. So we get the same answer. 2.70. I am messing up all over the place today. I'm blaming the sickness. I did promise I'd show you the easier way to do this problem. And it's quicker, but it takes more effort, I should say. In short, you don't need to break apart your triangles if you can keep track of what you're comparing. H I'm going to say is the short leg of the green triangle, so I must match it with the short leg of the big triangle, which is 3.1. H over 3.1. Similarly, in the green triangle, we have 5.5 as the hypotenuse. In the largest triangle, the hypotenuse is 6.3. So 5.5 over 6.3. Wouldn't you know it, we end up with the same equation without having to do all of that legwork of constructing these triangles. So it really depends on what you're most comfortable with. If you can identify those corresponding parts at a glance, feel free to be careful. So let's take a look at exercise, let's label as exercise 4. Let's roll the third exercise, where we're solving for x. Once again, this is the same deal as the last problem. We should identify corresponding parts, set up a proportion. So I'm going to do A here, and then I'll have everybody else do B. Let's do it. For part A, we need to find x. Well, I'm going to say that x is the longer leg of this triangle right here. If x is the longer leg of this triangle, I should compare it to a long leg of the big triangle. The long leg of the big triangle is this one here, 4. So we can say x over 4 equals, I am now going to see the hypotenuse of this red triangle is 3. So I can compare it to the hypotenuse of the big triangle, 5. Once again, we just cross multiply and solve. 5x equals 12, because 5 times x is 5x, 4 times 3 is 12. X is going to equal 12/5. Try out part B on your own. Pause the video and give it a shot. How do we do? We should have gotten 60 over 13. But that's how we solve. Let's take a look back at our notes page, because this process is very long. I mean, in the shortest scenario, you have to do a lot of thinking about what compares to what. In the longest scenario, you've got to draw all 3 triangles. It's a nightmare. So I'm going to teach you a shortcut that works about 2/3 of the time. This shortcut is going to involve a new definition, though. That definition is a geometric mean. Well, what is a geometric mean? It's something that we would have never seen before. The geometric mean of 2 numbers the geometric mean of, let's call these numbers A and B. It's the value x that satisfies the following equation. The equation's a bit weird, so bear in mind that it is going to take some adjusting. The equation is A divided by x equals x divided by b. Those who are keen-eyed may recognize that this equation could be simplified. If we cross-multiply here, as we're allowed to do, we would get x squared equals a times b. This is the geometric mean formula. The geometric mean squared is a times b. So if you really wanted to, we could simplify it further by recognizing that we would just have to square root both sides. X equals the square root of a times b. It's the square root of the product of the two numbers. So before we do anything, let's do a brief bit of practice with this, because this is very weird. Let's say I asked you to find the geometric mean of 2 and 6. Well, we know to find the geometric mean, we can use any of those three formulas we want. But the most convenient is the geometric mean is the square root of a times b. So, we know that x is going to equal the square root of 2 times 6, which is the square root of 12. But remember from the last lesson, we have to simplify any square roots we get. What can 12 be simplified as? Well, it's the square root of 4 times the square root of 3, and the square root of 4 is 2. So, 2 root 3. Let's do it with the lesson. Let's take a look at example 3, which says to find the geometric mean of 24 and 48. This one's going to be a bit tricky because these numbers are going to get large. So let's try this. X equals the square root of 24 times 48, which is the square root of 1152. And that looks like a monster to simplify. Recall that as long as you can find a perfect square divisor of 1152, you will have no problems. It just might take you a little while if you don't find the biggest perfect square. So, let's tackle this problem. To do this, we should really ask ourselves, what multiplies to make 1152? And that's not something that most people know off the top of their heads. My recommendation is to use your calculator. Start with 1152 and start testing out what it can be divided by. We know that 1 times 1152 is always going to work. Does 2 times anything make 1152? Well, divide by 2 and see. 576. We could keep going with this too. Like we could test 1152 divided by 3 and, oh, it makes 384. Or 1152 divided by 4 and, oh, it's 288. But believe it or not, one of these numbers is a perfect square. To test perfect squares, just square root the numbers. 576 is a perfect square because we get a number, not a decimal. So, we know how to split up 1152. The square root of 1152 is the same as the square root of 576 times the square root of 2. And since the square root of 576 is 24, as our calculator showed, this is just 24 root 2. So the geometric mean of 24 and 48 is 24 root 2. Very nice. Alright, now that we know what the geometric mean is, we can finally take on our last two theorems, and the reason why we turn our paper sideways. Let's take a look back at this good old triangle here, ABCD. And let's say for a moment that I wanted to figure out the length of BD. Well, I could compare it, right? I could set up a proportion. BD is the long leg of this red triangle. So what's the long leg of the, BD is the long leg of the red triangle. So what can we compare it to? We can compare it to either the long leg of the big triangle, or we can compare it to the long leg of the green triangle. I'm going to compare it to the long leg of the green triangle. So BD over DC. Well, what else could we compare? If we're comparing red to green, let's compare the short leg of red to the short leg of green. The short leg of red is AD, it's right here, and the short leg of green is BD. Wait a second. Doesn't BD appear twice? if we multiplied this out, we would get BD squared equals AD times DC, which simplifies to, when we square root both sides, the square root of AD times DC. Oops. Sorry, I'll get my letters all mixed up. Take a look at this, folks. This is a geometric mean. It's x equals the square root of a times b. In this case, we can say the altitude of this triangle, which I'm going to write as the word altitude, equals the square root of AD and DC are both the segments of the hypotenuse. So we're going to call it hypotenuse segment 1 times hypotenuse segment 2. This is just in words. The altitude, BD, is the square root of this piece of your hypotenuse times this piece of your hypotenuse. Nice. In words, it would look like this. The length of the altitude equals the geometric mean of the two segments of the hypotenuse. Very nice. Let's look again at this figure. We recognize that could also work with the legs. We compared BD to AC, BD to DC, I should say. But we could have compared instead BD to BC, the short leg of the green triangle to the hypotenuse of the green triangle, and the short leg to the hypotenuse of the red triangle. We can also compare the legs of the triangle. So let's take a look at that. If I wanted to compare the legs of these triangles, here's what I would do. I would compare AB, which we recognize as the short leg of this entire triangle. AB is the short leg here, to AD, for instance, the short leg of the red triangle. Well, AB over AD would be the same as me comparing the hypotenuse of the big triangle, which is AC, to the hypotenuse of the red triangle, which is AB. Wait a second, we end up with the same thing. We get a geometric mean. AB squared equals AC times AD, which means that AB is the square root of AC times AD. In plain English, it would look like this. The leg of your big right triangle equals AC is the entire hypotenuse, so this is the entire hypotenuse, times what we call AD. Well, since AD is next to AB, we can call it the adjacent hypotenuse segment. The leg of the right triangle here, the big right triangle, is the square root of this small part of the hypotenuse times, the entire hypotenuse. So the theorem would go like this. The theorem here says that the length of a leg of a big triangle equals the geometric mean of the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. The length of a leg equals the geometric mean of the hypotenuse, and the segment of the hypotenuse that's adjacent to the leg. Let's take a look back at our exercises and see what we can do here. So, find the value of each variable. We have two theorems to work with. And the first question we must always ask is, are we trying to involve the altitude, or are we trying to involve the leg for this problem? Well, in A, it's clear that the altitude is being used because it's what we're trying to find. It's x. So our theorem said, I'll put it in English again, the altitude is the square root of our two pieces of the hypotenuse multiplied together. In other words, x is going to equal the square root of 6 times 3, or the square root of 18. And what's the square root of 18 simplified to? Well, 18 is 9 times 2, and the square root of 9 is 3. So this is just 3 root 2. There we go. For B, the question we ask is the same. What theorem should we use? Are we involving the altitude or the leg? Once again, since the altitude is given to us, and we're trying to find a piece of the hypotenuse, it makes sense that we use the altitude theorem. It says the altitude equals the square root of the product of the pieces of our hypotenuse. Now this one's going to be quite a solve because, unfortunately, our y is under a square root. So we do need to square both sides. The square root of 18 is 324. And we can divide by 12 on both sides to get our answer. 27 equals y. There we go. Part C, we ask ourselves, what is involved? The hypotenuse, or sorry, not the hypotenuse, the altitude or the leg? This time, the leg is something that we need to find, so let's use the leg theorem. The leg theorem was the trickier one. The leg equals the square root of the entire hypotenuse times the adjacent segment of the hypotenuse. So, y equals the square root of, what is our entire hypotenuse if we know these two segments? Well, 2 plus 5 gives us 7, so 7 is the whole hypotenuse. And what's the adjacent segment, the one that's next to our leg? Well, y is touching 2, so it's 2. Y equals the square root of 14. which, believe it or not, is as simple as it gets, because there are no perfect squares that can divide 14. Now, I will say, for part E, things get a bit weird. It's weird in the sense that we are trying to find our altitude, but we don't know the lengths of our segments, or hypotenuse segments. Unfortunately, folks, this is where setting up just a good old-fashioned proportion works best, just like how we did in problem 2 and in problem 4. I'm going to say that X is the long leg, X is the long leg of this triangle here. The long leg of the entire triangle is 36. The hypotenuse of the small triangle is 15. The hypotenuse of our big triangle is 39. So we would get 39x equals whatever 36 times 15 is. If we do that math, 36 times 15 ends up being 540. So x ends up being 540 divided by 39, which is around 13.8. That's one way that I would do this type of problem. You could still technically set it up in a way that gives you a geometric mean. It's just tricky because you have to compare the left triangle to the right triangle. I'm going to show you the setup for it, and it will give you a square root as an answer, which is nice. The long leg of the right triangle versus the long leg of this triangle. Oh, actually, my apologies. We wouldn't be able to compare it. So, never mind that. Let's pause the video and try D and F. So pause the video here and see what you get. How did we do? These are, the answers for these parts. So if you have any questions, feel free to ask me. But otherwise, have a fantastic night.